All right, thank you very much, Rob. Um, I do a lot of things. One of the things I've been doing recently is work on Roughtime. And Roughtime is a new lightweight protocol for time transfer. Let's see how this clicker works. It works. And as most of you already know, having the correct time is not important just for keeping our appointments, but it's also really, really important for, I would say, almost all security critical applications that we have out there. I have a couple of those listed on the slide here as sort of an example. The first one is DNSSEC, which we use to sign DNS responses, right? And these signatures in the DNSSEC contain a timestamp. And that timestamp allows us to check that someone isn't passing us an old DNS reply, for example. So we can really check that it's fresh. And able to do that, in order to do that, we need to know what time it is, right? And also we have TLS, and pretty much all of internet sort of builds on the fact that we have TLS. So pretty much every website we surf to, every email that's been transmitted almost, is being protected by TLS. And every time we do a TLS handshake, we get a certificate from the server. And we need to check that this certificate hasn't expired. And we need to check that it hasn't been revoked. And when we do that, we need to know what time it is. And there's a bunch of other protocols as well that sort of depend on TLS, and I'll mention another one later. Apart from that, we also have a bunch of systems that do authentications on networks, right? So we might authenticate ourselves as users, or a system might authenticate itself to an authentication server and get a token. And then we present that token to a second system to gain access to it. And we may also have two-factor authentication systems to really make sure that we're the correct users. And in order for those systems to work, and in order for sort of bad actors not being able to take or steal old tokens and present them as new, we need to be sort of have some idea of what time it is to verify that the tokens we're presenting are tokens that are valid right now and not yesterday. There's also a bunch of cyber physical systems out there, and the one example I like to use there is door locks. So we might have an electronically controlled door lock, and that lock we may want to have it so that it's maybe open for customers during daytime and then closed during nights. And for that to work, we need to know what time it is, or the lock needs to know what time it is. And if a bad actor could, for example, sort of switch that lock's sort of idea of what time it is, then they could potentially use that to make it open when the actor wants it to open. So that's a security issue. And then we also have, and I think others have mentioned this as well today, logging, right? We need sort of, when we do security logging, we need a good time reference to be able to work out afterwards when something has happened, in which order things have happened, and cause and effects relationships. So what happened first, and what did that cause later on? So this also sets requirements on accuracy, right? So especially logging in computer security, we might need milliseconds or even microsecond level accuracy to be able to work out in which order things happened. And if we look at this from sort of an information security, a more theoretical standpoint, we can really lose sort of all the key information security properties if we have bad time. So if we have bad time and that leads to us accepting expired or revoked certificates or authentication tokens, that may lead to unauthorized people being able to log in, and we lose confidentiality and integrity, meaning someone can read information they're not allowed to, or someone can change information they're not allowed to. If we have the wrong time and that causes us to reject authentic tokens and authentic certificates, that causes loss of availability, right? We're getting stopped from logged in, we're getting stopped from being logged in, although we're authorized. So that's a loss of availability. And finally, if we have the wrong times for a log server or log files, they become inaccurate or maybe even ambiguous. and we can no longer make out what's happened, so we lose traceability. So in other words, pretty much any system that's secure needs to be able to keep time. And luckily, almost all systems can't keep time, at least when they're on. Very small devices, such as the one pictured here, they can't keep time when they're off. So if I pull the cord out there, it goes blank and resets to, in this case, 1970. Larger devices, so servers, personal computers, etc., they have these integrated real-time clocks, right? So they can still keep time even when they're off, and then sort of keep on going once they go on again. And the problem with sort of all clocks, whether we're talking atomic clocks or whether we're talking these sort of cheap real-time clocks in PCs, is that they drift, right? So they're accurate up to a point when we set them, and then from that point on, they sort of drift more and more and more, which means we need to continuously update time. And one way of doing that is, of course, we could just manually reset it once in a while, but that really doesn't scale when we have big infrastructures, and then of course users really don't like doing things manually. So the way we do that is that we get time over the network, and that's more or less a solved problem. We've heard a lot about different ways of doing time transfer this afternoon. The gold standard to do this over networks, over IP networks, is NTP. It's really an excellent way of doing it. You can easily get sort of sub-millisecond accuracy just with a good NTP setup, and if you have sort of good symmetric ping times over your network. The problem with NTP is that it's often used with only a single server and often used without authentication. And the problem with using NTP with just a single server, known as simple NTP, is that we have no way of telling if that server goes bad. So if that server's time starts drifting, and that can happen if the server loses its connection to its time source, so maybe a GNSS receiver or an atomic clock. And that's been known to happen, that sort of the NTP server starts drifting, and suddenly we don't have the correct time anymore, although everything seems fine. And that's something we can prevent by actually asking several servers for time, right? So then we can make out if one of them is bad, and we can reject that. And as I mentioned, NTP is also often used without authentication. And the problem there is we have no way of telling who actually sent us a time response. It might be the server we sent the query to, or it might be some on-path attacker that sends responses instead of the server we want the response from. And it turns out this is actually pretty common. A lot of ISPs do this for all their customers. They intercept NTP queries from their customers and send their own replies. And I think most ISPs think they're doing a good thing here, right? They're providing their customers with time from a closer server. The problem is that the customer doesn't know this, and more specifically, the customer has no idea that. So they may think that they asked 10 different servers and got 10 different replies back, but in reality, they got 10 replies from the ISP server, right? So now they're using a single server without knowing it. And NTP has a solution for authentication, and that's symmetric authentication. And the problem here is that client and server need to share a secret key. And that works within an organization. You can manually assign secret keys to your NTP server and to your whoever needs to use NTP. But it really doesn't scale beyond that. So a modern NTP server that serves clients on the internet can have literally millions or tens of millions of clients. And it's obviously impossible to provide clients with tens of millions of symmetric keys manually. NTP also has something called AutoKey, which is sort of an attempt at public key authentication. The problem is it's broken. It's horrendous. Don't use it. Luckily, since 2020, We have something called Roughtime Security. I'm a co-author of the RFC that defines that. And what NTS does is that it adds security to NTP that's scalable. So it makes it possible to provide authenticated time to pretty much anyone that needs it. I know Rice mentioned that they're among the organizations that provide NTS services, so does Netnod, and so does meteorological institutes in other parts of the world, such as Germany. And NTS depends on TLS. So to set up a shared secret between an NTP client and an NTP server, it uses TLS handshakes to generate those secrets. And the problem here is that to make a TLS handshake, we need to verify a certificate which requires correct time. But we're making the NTS handshake to be able to get time, right? So we have a bootstrapping problem here. And it turns out you really can't get secure time without running into some sort of problem of this type. TLS also requires a sort of a list of up-to-date certificates from certificate authorities, and that list can actually be quite big, large enough to not fit on a small device such as the one shown here. Another sort of unfortunate problem with NTS is that it has low adoption. So I looked at Netnod's statistics the other day, and I think about 0.5% of requests to ntp.se are NTS protected. So 99.5% or so are completely unauthenticated NTP requests. And a big reason for that, I think, is that there's low adoption in operating systems. It took a long time for operating systems to support NTS in their NTP clients. Recently, we've seen a lot of Linux distributions that now ship with NTS supporting NTP clients. So if you run on any of those, actually upgrading to NTS should be as simple as changing 1 or 2 lines in the configuration file, and then you'll be running NTS immediately. So that's quite nice. But what I'm here to talk about today is Roughtime. So all of this has been leading up to me talking about Roughtime, which is sort of a solution to the edge cases that sort of NTS and NTP doesn't fit. And Roughtime is a protocol that's currently an IETF draft. I'm a co-author together with Watson Ladd, who's at Akamai currently. And the way I've been told the story is that it sort of started out within Google, because Google saw through telemetry in Chrome that the main reason for certificate validation failures in Chrome web browsers is that the user's clock has the wrong time. So they needed a way to sort of verify that independently, that was secure, and also would scale up to the amount of users of Chrome there are, so in the hundreds of millions. Turns out they're not actually using Roughtime. I don't know what they're using. But it ended up in the IETF instead, mostly because it's sort of a good fit to try and solve sort of the bootstrapping problems with NTS, and also as a way to securely get time for resource-constrained devices. And I really want to stress that it's not intended to replace either NTP or NTS, but rather sort of fill those edge cases where they don't do the job. And in this context, Netnod has received funding from RIPE to help sort of finish the development of Roughtime, make it into a working protocol, and move the draft towards becoming a standard, an RFC within the IETF. So some key concepts about Roughtime is that servers have these long-term public keys. So keys, the keys are basically the same key is basically meant to be used by a server forever, or as long as it's in use. And those keys are sort of the anchors of trust. So a client places its trust in these keys. And this turns the bootstrapping problem in NTS to sort of a key distribution problem instead. So as I said, we always run into these problems. We can just sort of choose which one we want to have and handle in our particular situation. And those keys are used to do public key signatures using ED 25519, public key signature standard. The problem with public key signatures is that they're slow. They're really, really slow. And a typical NTP server, a big NTP server on the internet, can get over 100,000 queries a second. And if you're going to do 100,000 public key signatures, you're going to need a lot of computing power, a sort of almost prohibitive amount. And the way Roughtime handles that is that they use a cryptographic construction called Merkle trees. And Merkle trees allow us to batch these signatures. So we can take, a server can take several thousand requests. And using a Merkle tree, then only make a single public key signature for all of those 1,000 requests, which really saves on computing power. A client then asks multiple servers for time, and it does that sequentially, so one after another, and can check that those responses are consistent, because time should be increasing, right? And this then removes the possibility of a single server failing or a single server sending a malicious response. And together, asking multiple servers, as well as the public key signatures and these Merkle trees, give another sort of key benefit with Roughtime, and that is that it's possible to cryptographically prove that a server has done something bad. If a server sends us bad time, we as a client can create a cryptographic proof that that happened, even if it just happened once. And this isn't possible with NTP or NTS, so this is unique for Roughtime. And some details, this is sort of the only slide with a weird figure, so some details on that. It works as in all timing protocols with a client sending a request and a server sending a reply, and the reply obviously contains the current time. Roughtime also sends what's called a radius, so basically an inaccuracy in seconds, like plus or minus 2 seconds. And the server guarantees that the time is somewhere within that gap, so say plus or minus 2 seconds. And that's sort of the only guarantee we get from Roughtime, that, well, it's somewhere in there. And what's also included is part of this Merkle tree, which I won't go into explaining what it is, and a signature. And since the client has included a nonce, a random number in its request, it can check that was included in the Merkle tree and signed. So that's how it can sort of check that all this is valid. And this construction also makes it possible to chain responses. And this is what this UML sequence diagram is trying to show, right? So the client on the left has generated this random number, sent off a request containing that random number to server 1, which then sends back a signed response, and the client can verify that it includes this random number it sent. It can then hash server 1's response, include that hash in the second request to server 2, get back a new response from that server, hash that response, and do the same with server 3. So these are chained, and if we save the requests and responses, anyone can verify that they happened in that order. So if server 2 here in the middle has sent us the wrong time, a time that's either before server 1's time or after server 3's time, we can verify that cryptographically, as long as we trust server 1 and server 3. And we can do that with any number of servers and in any order to make sure that no one is cheating us, or conversely to detect if someone is cheating us. And it also, and this is also can be quite useful for some applications, we could use this to sort of timestamp any sort of data we want. So we get for free with this standard a general timestamping service. So I've been dealing with Roughtime for a couple of years now, and it's evolved to the point where it's a fairly decent generic time protocol that's secure by default, that doesn't have very large CPU requirements, has small memory footprint, there's no state stored on servers. We can use it to prove if a server does something bad, even just once. And we can use it to timestamp arbitrary data. Recently, last year in November, we were at IETF in Dublin, participated with Roughtime in the hackathon there, and mostly the intent was to do interoperability testing. But we also, thanks to the discussions there, discovered security issues in the standard that we were able to fix in the next draft version. Thanks to the interoperability work, we also made sure that the 5 or 6 major implementations actually could interoperate, and we found bugs in most of them, preventing some interoperating cases. But they were all fixed actually during those 2 days. Moving forward, we intend this to become an experimental RFC within that process in the IETF. And literally any day now, hopefully tomorrow actually, we should get a working group last call for the Roughtime standard, indicating that the NTP working group is done with it and is ready to move on in the IETF process to becoming an RFC. What also needs to be done is we need to update implementations, specifically regarding the security changes we had to make in November. And there needs to be a robust ecosystem. For Roughtime to work and be successful, there needs to be a fairly large amount of servers and, of course, also good working implementations. So if any of you are interested in trying out Roughtime yourselves, here are some implementations of it. Cloudflare has both a server and a client implementation, and they're probably the most popular ones that are used out there. Cloudflare also runs servers. There's Craggy, which is this C implementation for really tiny platforms. So you can run this on, for example, the TT Go I showed earlier. I have a Python library, both a server and a client library. And the idea there is that the client library should be very simple. You should basically have a method, call that method, and get back time you can trust. There's a Rust implementation in Rough Enough, and I also have a Linux daemon implementation for running a typical Linux server. Most of the clients come with lists of servers in a standardized JSON file, so you should be good to go immediately. And if not, you can just use my server, go to roughtime.se, all the long-term keys and everything is there. So it should be fairly easy to use. That's pretty much all I had for you. I hope you learned something about Roughtime, and thank you very much.
Thanks, Marcus. Do we have any questions for Marcus on Roughtime?
Thank you. So I'm Stefan Alfredsson from Karlstad University. So I was thinking of the bootstrapping problem. Could you do a hybrid approach where you first get an NTP query and then an NTS query? So if you get roughly the right time, even if it's faked, even if the operator has man in the middle that hacked you, then if you would validate the certificates, that would be fine.
Yes. So in the RFC for NTS, we discussed this and we have a long list of recommendations. And the currently best way of doing it is, get NTP or even do a full NTS handshake. Just ignore the fact that you don't know what time it is. Yeah. Get time and check that everything works out afterwards. That's in short the recommendation we're making.
Yeah, great, thanks.
Yes, question on Menti. The final sprint of the day.
So what if the baddie runs a lot of Roughtime servers serving bad time?
Use more Roughtime servers. Actually, there's other research on that. There's something called Cronny. A bunch of Israeli researchers did this for NTP. They basically looked at how can you statistically defeat that. And it turns out, if you get a smart statistician, you get around it that way. You literally get a very large amount of servers and randomly ask them. That's the trick to it. There needs to be more good guys than bad guys, in short.
Okay.
We got a segue question for Rob. When will there be time for beer?
The time for beer is mostly upon us. So let's thank Marcus for a fantastic presentation on Roughtime. Thank you.
Thanks, Rob.
Thanks.